Okay, so we've been through substitution elimination, and so in addition to just these being mechanisms that you have to learn, which is its own challenge, that it has all these different types of things that we've learned for our other reactions, the stereochemistry, the radioselectivity, all these different types of things. We also have to consider that these mechanisms compete with one another, and that's what makes this section sort of challenging. So when are things going to go SN2? When are things going to go E2? When are things going to go SN1? When are they going to go E1? And so I think the way to kind of get at this is one, we're going to look at the substrate. I think this gives you the most information about which direction the mechanism is going to take. And then second, we would look at the reagent. And here I'm talking about, the it's either going to be a nucleophile if it's behaving in a substitution, or if the mechanism is substitution, SN1 or SN2, or is it going to be a base? And how do we know? How do we know which one it's going to be? It can sometimes be a little bit tricky. And then the third thing you can sometimes consider is the solvent. And I'm gonna put that off for a little while because we've got enough things to think about. Okay, so let's see. How do we want to go about this? So let's talk about the substrate first. So we've already kind of looked at this. So our substrates, ignoring allylic and benzylic, which are special cases, which I discussed in a different video. Generally, you're looking at things that are either primary, secondary, or tertiary. And we know that SN1 and E1 tend to prefer things that are in the direction of tertiary, and SN2 generally prefers things that are in the direction of primary. And E2, what does E2 really favor? Yeah, I would say E2 generally is going to be kind of grouped down here towards the SN1 and E1. E2 is a little bit weirder in that you can kind of see it operate all over the place. So I would say it trends more towards being at the bottom by the tertiary, but it's not always the case. You can sometimes get E2 elimination for primary, and we'll talk about that. Okay, so yeah, you can kind of get a feel for this. It's kind of rough. Actually, I'm just gonna, let's just say E2 can happen for any of these. Okay. But yeah, you can get a feel that these things are kind of rough. It's kind of difficult to make predictions. When you've got things that are primary, they almost always undergo SN2. So if you're looking at something like this, as long as you put something in there that's nucleophilic, be it a base, whether it's basic or not, you're generally going to see substitution here, and it's going to be SN2. But then as you sort of move down to getting to secondary, here you can see SN2, or it can be SN1, E1, or it can be E2. So secondary is probably the hardest one. And then tertiary, you can have, you never get SN2 in a tertiary, so that's ruled out. But you can get SN1, E1, or E2. Whether it goes between primary, secondary, or tertiary whether it goes SN2, SN1, E1, or E2 is dependent on the substrate. That's kind of your first clue. And then the second clue that you have to look at is the reagent. So like in these cases, if I look at this case, the substrate doesn't really give me that much information, because really it could be anything. So if I'm looking at a substrate like this, so all I've done is taken the original substrate that we looked at up here. I like to put the methyl groups on the edges here, just for style reasons. But yeah, if I look now at this secondary substrate, Yeah, is it going to go SN2, SN1, E1, or E2? That's going to depend almost entirely on the reagent. Okay? But then if I look down here at this one, let's say now I'm looking at a substrate like this. Okay, well, I know it's not going to go SN2 because it's a tertiary, and that's helpful. But how do I know if it's going to go SN1, E1, or E2? You'll notice that when I'm writing this out, I'm writing SN1, E1 like this, and that's because these two mechanisms generally appear together. And usually the one will be favored more than the other, and there's some rules for trying to predict that. We're not going to worry about that. We're just going to group them together. So ostensibly it looks like you're trying to predict the products or what mechanisms the reaction's going to go through from 4 different mechanisms, but really you're looking at 3 different mechanisms because 2 of those mechanisms always appear together. Okay, and we'll talk more about that as well. Okay, so yeah, so substrate sort of gives you your first clue. Okay, so you can kind of start to say some things immediately. If you see that it's primary, then you know it's going to be heavily favored towards SN2. If you see that it's secondary, it's kind of like I have no idea what the hell's going on. And then if I see that it's tertiary, I can at least rule out SN2. That's how I start out this analysis. And if you look in your organic chemistry textbook, the one that we have, I think is free now on CEngage, you can find a little flow chart. And our tests are open notebook, so naturally, if you need to answer these questions, you guys are, I'm sure, competent enough to just go through the flow chart and kind of analyze what's going on here. We sort of have this luxury, I guess, of being able to take it a step further because you're not going to be forced into as much memorization here, and we can kind of consider why is it that primary always goes through. Why is it that this is always true? Why is it primary generally favors SN2, and why is it that it's never for tertiary? And we've talked about this already in some of the other lectures, but we're gonna hit that again because I think that's sort of the real lesson here is sort of understanding not just what mechanism these things go through, even though that is powerful, is understanding why does it prefer these mechanisms, because then we can use that to extrapolate to other types of reactions and mechanisms to understand things. Generally in organic chemistry, electronics, which would be something like carbocation stability, or sterics, which is what we're talking about with SN2 reactions, dictate most reactivity. Unless you're dealing with radicals or transition metals or something, you can say a lot of stuff by just making arguments around the electronics and the sterics. Okay. All right. So yeah, so the reagents. So this is part of the thing that makes this tricky is that remember that good nucleophiles, or good bases, I guess I should say, are also good nucleophiles. And if you're looking at elimination, there your reagent is behaving as a base. And if we look at substitution, if you look at substitution, there our reagent is behaving as a nucleophile. So if you have a reagent like OH-, which is a strong base, which means it's also a good nucleophile, how can we predict which one it's going to behave as in a reaction? So this is when we tie things back into the substrate, which is what we analyzed in the last situation. So I've already shown you the results of this reaction. What are the 2 real competing reactions here? So we know that a primary substrate never goes through SN1E1. So it's not going to go through SN1E1. Why is that? primary carbocations are very, very unstable. Okay, so just the barrier to getting through to forming those primary carbocations is extremely high. And so SN1E1, these are slow reactions. They just don't really happen unless the primary carbocation that can form is very stable, or reasonably stable for being a carbocation, and your nucleophile and base or base is weak. So pretty much everything here is geared against SN1E1. This thing, right, our substrate is primary, so that doesn't favor SN1E1 because it's going to form a really high energy carbocation. And then this is a strong base. And in order for SN1E1 to be competitive, you need a weak base or a weak nucleophile, right? So this is a strong base. Well, I guess we already wrote that up at the top. No need to rewrite it. But yeah, so this is a strong base and a good nucleophile, so that disfavors SN1E1. And then this is primary, which won't form a very good carbocation, right? Because we're saying that primary carbocations are generally really high energy. So that also disfavors SN1E1. So when you're kind of doing your analysis, you're not just considering what makes one reaction better than another. You have to consider what disfavors other reactions. And I kind of tend to just start with what is disfavored. I don't know, it just seems like an easier place to start the analysis. Okay, so we know SN1 and E1 won't work. All right, so now we're looking at, once you've ruled out that, you're saying SN2 versus E2. So what favors SN2? Strong nucleophile. And what favors E2? Strong base. So here our reagent doesn't help us. It's not useful by itself. We have to consider our substrate as well. Oops. And our substrate is primary. Primary strongly favors SN2. And why is that? Remember that in a primary substrate, you just don't have a lot of steric hindrance. So it allows our nucleophile to actually behave as a nucleophile and come in here and interact with that antibonding orbital and kick off the leaving group. Okay? So why doesn't it go E2? Because it's also a strong base. So this also seems like a reasonable reaction to have to form the alkene. You could say, well, why doesn't it go that direction? And the answer to that question is just that it probably does. This is probably a very minor product. But the reason it doesn't happen, why that's not the major product, is because the primary substrate allows for this reaction to happen very, very fast. So the SN2 reaction is really, really, really fast, and it just outcompetes the E2 reaction. So that's kind of how you're trying to think of these things. And so, yeah, you can see, as I'm saying this out loud, I'm realizing that these analyses are like pretty complicated. And that's sort of the power of being able to use a flowchart. I think the important thing when you're sort of going through these is to make sure that you understand the breaks in the flowchart. Why is it that one thing favors the other? You should be able to make these arguments of like, well, they're sterics, or the carbocation's not stable. Those are the types of lessons you really want to take away that you're going to carry with you throughout this course and through the next course. Okay, so that's for a primary. Let's see what happens if we change things up, though. So what about our other substrates? Remember, in the secondary case, let's say some other things about the primary case. Yeah, let's just beat the primary thing to death, and then we'll move on to secondary. So I'm at 15 minutes right now. Okay, if we wanted to, let's say we wanted to favor this product, how could we favor E2? Okay? So you can kind of see how I approach these things. It's not just like decision making. Let's say that you're actually trying to do one of these reactions and you want this thing to go E2. How would you do that? Well, you're kind of stuck with your substrate. There's not much we can do with this, right? So one answer would be, well, I'll just use a different substrate. Well, if this is the product that you want for whatever molecule you're building, you can't just change the substrate. That's not really allowed. So what else could we do, though? Well, what makes SN2 so competitive, it's that the nucleophile can very easily access the antibonding orbital on the substrate. We can't change the substrate, but we can change the nucleophile. So if I make the nucleophile something big, like terbutoxide, now suddenly this reaction starts to slow down. Because yeah, it's primary, which means that this is about as open as that can be. You know, this antibonding orbital that's located right here on the back, as it's about as accessible as can possibly be. But if my reagent that I'm using is extremely sterically bulky, now that reaction is going to slow down because sterics ultimately dictate whether something can go SN2. So all of your arguments around SN2 fall back on sterics. The more sterically hindered something is, the more it's going to slow down our SN2 reaction. Okay, so now this is slow. This is slow. I gotta be careful with my arrows here. This is slow because sterics. And now we can make E2 more competitive. And pop that off. And we get our alkene out. And indeed, I would expect this to be the major product now. And so you can think about it, when I change the nucleophile slash base here, from hydroxide to terbutoxide, what's the effect on SN2? It slows it down. What's the effect on E2, though? It doesn't have any effect on E2. It's still just a strong base. It's just that SN2 is now slowed down so E2 can win the race. So it's important not only to think about what favors a particular mechanism, it's also important to, it's almost equally important to consider what disfavors the other mechanisms. So SN1 and E1 are immediately just not allowed inside of a primary, when you have a primary substrate, with the one exception of it being allylic or benzylic, which is covered in a different video. It comes down to, is it going to be SN2 or E2? And generally speaking, SN2 will be favored unless you really work at it and you really want it to go E2, and then you use a strong base that is also extremely sterically hindered, and then you can kind of force it to be E2. Because you can slow the SN2 reaction down enough to where now E2 can win that race. Okay? Okay, so that's primary. Primary is the simplest case. So generally, if you have to guess, primary is going to go through SN2. You should try and work through this rationale here of like, what is changing one piece of the reaction due to all of the different competing mechanisms? So now let's look at those same things, the same exact reaction, but now instead of tinkering with the reagent, we're going to look at a different substrate. So nothing has really changed here about our reagent. It's still a strong nucleophile. Let's take a look at our reagent. Still a strong nucleophile. Still a strong base. But our substrate now is secondary. What's the main effect of that going to be? It's going to make SN2 slower. Secondary substrate slows down. Well, let's actually go through it and try and be a little bit more systematic. Oops. Secondary substrate. So, yeah, what can we say about that? How do we want to go about this? Let's go through, let's just start with, like we did in the other problem, we'll start with SN1E1. And then we'll go to SN2E2. Okay? Because generally things that SN1E1 and SN2E2 are sort of like two separate problems. It's rare to have all three mechanisms sort of having a chance at it. You can either rule out SN1E1 immediately or rule out SN2E2 immediately. Okay, SN1E1. Is this possible? Well, the substrate, secondary carbocations are, I would say, like stable enough. So the substrate makes me feel like, oh, okay, maybe it could be SN1E1. But then I come over and I look at my reagent. Does that favor SN1E1? Well, if SN1E1 is going to happen, we know that the first step in the reaction has to be that the leaving group just pops off. And the only way that can happen is if you have a very weak base and or a very weak nucleophile. So having a strong base or a strong nucleophile eliminates SN1 and E1 as a choice, generally speaking. Okay? So we're going to say not possible because we have a strong base, strong nucleophile. So you can think of SN1 and E1 as being like if all of these guys are racing. You know, we have SN2, we have E2, and then we have SN1, E1. They're sort of like they're all in the same like track meet or whatever, but for some reason they're like tied together like a three-legged race situation. So this is always slow. I keep trying to want to make that a T. This is always going to be slow. So in order for SN1 and E1 to win, SN2 and E2 have to be slowed down. That's sort of what's going on here. SN1 and E1 is never fast. It's just that you can make SN2 and E2 slow enough that SN1 and E1 can now have a chance in the race. They're like just the shitty racer who hopes that the SN2, E2 go out and get really drunk the night before the race and can't make it through. So if anything disfavors SN1, E1, it immediately goes somewhere else. So things really have to line up well for that. So SN1, E1 doesn't happen. And the reason it doesn't happen is because we have a strong base and a strong nucleophile. And that just makes the other reactions too fast. So SN1 and E1 can't catch them. So then it just comes down to trying to figure out which one of these it'll go to. Now we have SN2 versus E2. Okay. This is where things get very dependent on what the reagent is. if the reagent is a base, so if the reagent is a strong base, then E2 is faster than SN2. So let me go down here, I'll say E2 let's go through, I'm sorry guys, I keep jumping around, this stuff's kind of hard to explain. Let's go through SN2 first actually. So the base thing is going to come into play, but let's look at SN2. So SN2 is slowed down, so it's plausible because the sterics are like in a middle ground. They're not so bad, but they're not great. So it's plausible. The thing that tells you whether or not SN2 is going to win is not possible if the reagent can be a strong base. And this is just like we saw in the last one. So SN2 and E2 are in competition here. Let's say that they're both, with the secondary substrate, both are completely plausible. And they're both going to be kind of running at the same speed. And then we look at our, whatever our reagent is. If our reagent is a strong base, that's going to favor E2. It makes E2 faster than SN2, not because, God, this is such a confusing way to put this, but it's not because E2 is actually getting faster. E2 is not running faster. It's that SN2 is slowed down by the substrate. So now E2 is the fastest, is probably the right way to say it instead of faster. So E2 becomes the fastest in the race. So ultimately, what you end up with here is just the E2. And so I think if you, I don't know what it says in the textbook, generally what we're going to ask you about is just whatever the major product is. Yeah, would you expect some minor product that's SN2 here? Probably. But that's not something we're going to worry about when we quiz you. So you end up just getting the alkene out here. Okay, so if you look back at the last example that we worked through, we were saying, and where we kind of forced it to go E2, we switched up the nucleophile / strong base to just be super sterically bulky. And that slowed the SN2 reaction down. So a bulky nucleophile / base slows the SN2 down and makes the E2 the fastest. Here, our base is very small and not nucleophilic, and not sterically hindered. But our substrate is now sterically hindered, which slows down the SN2 reaction and again makes the E2 the fastest. So even though these things seem like, almost unrelated, they're identical sort of reasoning here. So if sterics are present in any way, and you have a strong base, then you can favor E2. That's what's going to be favored. That's sort of the lesson there. What happens if I switch out to terp butoxide? Like we did in the last one, we're still just going to see this alkene. It's just that, because now we've got this, which is very sterically bulky, which disfavors SN2, and we have this, which also is going to disfavor the SN2. It's going to slow it down. And so the result is, again, just going to be what we expect, which is the alkene. So maybe if you're seeing, if you're running this reaction in the lab with hydroxide, and you're trying to get the E2 product, if you want to, and you're seeing a little bit of minor substitution pattern or something there. You're seeing a little bit of SN2. You switch over to terp butoxide, and then you probably just see complete elimination. You're not going to see any kind of side product there. Okay? So this is the trickiest one. When does this go? What happens if we keep changing our reagents, though? Okay, so both of these are strong bases and necessarily strong nucleophiles. What if we switch it up to where now we don't have a strong base? Let's say that we just use something that, let's say we use something like iodide. So iodide is a good nucleophile. We also know that it is not a very good base. It's a very weak base. It's kind of like chloride or something. It's the conjugate base of a very strong acid. What are we going to expect here? So SN1 versus E1. Okay. Again, same rationale that we saw above. This not going to be competitive. Because the nucleophile is strong. Okay, so if anything favors SN2 or E2, either a strong base or a strong nucleophile, SN1, E1 is always going to be the slowest, and it's just not going to be able to be competitive. So now we come down and we look at SN2, and we look at E2. All right, for elimination to take place, we need a strong base. If we don't have a strong base, we just don't see E2. So I'll rephrase this. This is very slow without a strong base. So SN1, E1 is super slow, and we have a strong nucleophile there, so that immediately disqualifies that. A strong nucleophile, or a primary substrate, or a strong base, all immediately eliminate SN1, E1, because it's too slow to compete with any of those, compete with the other mechanisms in any of those cases. E2 won't happen unless there's a strong base present. So all we're left with now is SN2. So strong nucleophile that isn't basic is what you need in order to have a secondary substrate, in order to have a secondary substrate undergo this reaction. Kicks this out. And we get this nice SN2 reaction. Okay, so that's how you see SN2. These are both E2 up here. All right. What if we wanted to get things to go SN1, E1? So in order to get SN1, E1 competitive, priority one is we have to have something that can form a stable carbocation. And we have that. We sort of established that previously. So secondary forms a stable enough carbocation, so we're good for that. But the other thing we have to do is we have to make sure that SN2 and E2 are not competitive. And how can we do that? So SN2 is competitive as long as we have a strong nucleophile. So we need a weak nucleophile. That'll disqualify SN2. Disfavors SN2. And then we have E2, where if we have a weak base, that disfavors E2. So if we can get a weak nucleophile and we can get a weak base, that slows both SN2 and E2 down enough to make this guy that is normally not very competitive suddenly a pretty good competitor, right? So we have SN1, E1 that are kind of bound together. They're the only guys doing a three-legged race for this thing, and this is the situation where they can suddenly kind of be the underdogs that take it all. So what does a weak nucleophile, weak base look like? Those are going to be the things that we established as bad nucleophiles when we were kind of working through what nucleophiles even were. And so methanol or water or some sort of protonated carboxylic acid all will go through SN1E1 here. So how would this happen now? If we draw out the full mechanism for it, that comes off. Oops. And then the methanol can come in. And then in the last step, of course, we deprotonate. And we get our product. So that's kind of how the analysis goes in the secondary one. So secondaries are the most complicated ones. They can go through any of the mechanisms, and it's very, very dependent on the reagent. But the reagent does dictate what goes on. And it's kind of straightforward to just look at the reagent and understand. So for a secondary, if we go back all the way to the top, if the reagent is a base, let's see, let me change colors here. Blue. If the reagent is a base, any kind of strong base, it goes through E2. If the reagent is not a strong base, but is a strong nucleophile, as is the case here, it goes through SN2. So other strong nucleophiles that are not basic would be something like this, like a thiolate or something like that. But not things like methoxide or NH2- or something like that. Those are not going to go through SN2, those will go through E2. And then finally, if we want to do SN1E1, we use a reagent that's not a strong nucleophile or a strong base. And that gives it enough time to go through this kind of weird mechanism where it forms a carbocation in the first step. Okay, so finally, we get to tertiary. What happens when we do that? So now, if we just put an extra methyl group on here, we can look at SM1 versus E1. So it's favored by the substrate. So it depends on the reagent. We know from our last example that we want something that's a bad nucleophile and a bad base. Needs a bad nucleophile and base. Okay. So this thing functions or becomes fast enough when the nucleophile and the base are bad. SN2 never happens. Never happens. And why is that? Well, now we're just in a situation where there's so much steric hindrance around whatever this little orbital is on the backside here, that no matter what the nucleophile is, it can't quite squeeze in there and make SN2 happen. And then E2, this depends on the reagent. And so what reagents are going to favor this? Strong base. Okay. So if I take a strong base, something like hydroxide, what am I going to see? I'm going to see the E2 product. So go in, it's going to take that off. I'm going to kick that out. If I have a weak base, let's say now I just use the protonated version of that, then what am I going to see? Oh, it's going to give me enough time here. I'm going to get SN1E1. So that's going to pop off. So yeah, some of this is going to go towards this. I didn't do this in the last one. I just drew the SN1 product. But some of it's going to be the E1 product. So you're going to get deprotonation. And then some of it you're also going to get, let me use a different color maybe. Some of it you'll also get, so a competing reaction mechanism with it. Actually, I'm just not going to draw that at all. But a competing reaction mechanism with it would be to form the SN1 product. And you just see those in some mixture. And again, certain books will try and dictate, which one you'll see more of. We're not super worried about that. Okay? But the main thing you want to be thinking about here is how tuning the reactivity of the substrate in the reagent affects the outcome. So you can just take any reaction, and there are many, many, many of these in the workbook, which I'll work through some of them. You can take any reaction and think about tuning it. So you could start with sort of the most basic reaction you can imagine, which might be like taking this. This has no choice but to go through SN2. And then start thinking about, well, what could I do to make it go through other mechanisms? So if I wanted this reaction to go through E2, how could I do that? Is E2 even possible? This reaction has no beta hydrogen, so no, we'd have to change our substrate. Would that be enough to make this go E2? No, we'd still see SN2 here, right? Because we talked about this. Primary substrates are not sterically hindered enough to make E2 competitive. If I wanted to force that through E2, I could either, or if I wanted to make this reaction go E2, I'd have to do either change the substrate, which would make it a different reaction. So now I've made E2 more competitive because I've slowed the SN2 down. And now I get this. Or I could stick with my original substrate. Instead of changing the substrate, change the nucleophile. And now I've made E2 more competitive. So you can kind of see how you can kind of work through this. What if I wanted to get SN1 and E1? What would I have to do in that case? Could I do that on the primary? Is that possible? This will never, even if I change, let's say I take a really, really bad nucleophile here, okay? So I've got this. It's a terrible nucleophile. It's a terrible base. This thing can't go through E2 because it has no beta hydrogens. What are its options then to react? If it's going to happen, it's going to have to go through SN1E1. But the primary carbocation that you'd form, or the methyl carbocation, is so unstable that you probably just would get no reaction here. If you wanted to make it go SN1E1, you could either take it and make the allele. Again, you're not really doing the exact same reaction when you change the substrate, but this is just to learn these things. Yeah, now that I've got an allele next to the primary position, now I can get SN1E1. Let's see. Well, actually, you won't see any E1 because even though we have a beta hydrogen here, the beta hydrogen is on an sp2 carbon, and it's unusual for those to go through elimination reactions at all. So probably what you'll see here is just this, and it'll go through SN1. What if we change the substrate to something like this, which is what we looked at before? Okay, and now we start to see SN1 and E1. Oops. And we'd also get the E1 product. Okay, so one way to learn this stuff is just to take, and I'm working through these incredibly fast. I'm gonna go through some slower in another video. But one way to work through this stuff and try to understand it is to just take one reaction that you know and kind of understand why it goes, let's say through SN2 or E2, and then try to change that reaction to make it go through a different mechanism. And that's one way to kind of understand what favors and disfavors all the different mechanisms. How do I make something go to E2? Well, I could change I could make the base stronger, I could change the steric situation, and that's a much more powerful way to kind of learn these things than to just follow the flow chart. Which is an acceptable way to kind of, if you really need to know what the reaction is going to turn out to be, a flowchart is fine. I'm just saying that there's a better way to kind of learn this stuff, and it's to not depend on a flowchart, but to try and look at the reaction and sort of develop an intuition around it. It's a harder way to learn it, but it'll stick with you better. Okay, I'll work some examples in another one. If you've stuck with me through this kind of long video, thank you for that. Yeah, I think the best way to get through these is to work a lot of problems. You can see there's a lot of nuance in these.